We've made some reference to the microscopic approach to entropy and how Boltzmann had these ideas to do with microstates having equal probability and how this could illustrate chaos and disorder and dispersal of energy. And so now we're just going to get into the detail and see what this work really amounts to. And actually, as we can see on the screen here, we'll be looking at this kind of a diagram where, to illustrate this really microscopic approach, we've got these three different color rectangles labeled A, B and C, and so these are going to represent individual molecules, sort of most basic units in a system. And you can see those little circles. Those little circles are representing microscopic packets of energy. So actually, when you get down to the molecular level, molecular excitations come in these discrete units of energy, which is obviously something we don't normally experience. We normally experience energy as a kind of a continuous thing. But at the basic level, not only is matter quantized into discrete molecules, but also energy is quantized into these discrete units, which we'll call quanta. And so it's using these ideas that we'll flesh out this theory. So in this microstate approach, we can kind of appreciate intuitively, if we think about diffusion, that ultimately molecules are likely to spread out in space if they're given the freedom to move. So that if they start off in a very concentrated way, they would disperse to a more dilute way. And likewise, if they started off in a very well-ordered condition, they'll probably end up in a disordered condition. And in fact, as far as energy are concerned, we can do a similar kind of a thing, because as I just said, energy come in these discrete little packets called quanta. And again, if we can arrange these probabilistically, then the chances are we'll get some kind of disorganized state of all the quanta of energy. So unlikely to be in a highly organized way. And so in our model, what we're going to do is we're going to assume that all molecules will have an equal likelihood of gaining a quantum of energy. Say a quantum is the singular of quanta, plural. And if a molecule already has a quantum of energy, it doesn't affect the probability of getting another quantum of energy. So actually a molecule could have no quanta or loads of quanta, and the chance of it picking up an individual quantum is not affected by any quanta it's already got. And so in this first approach, we'll consider the simplest possible case really, just two molecules, A and B, and two little packets of energy. And so these are shown here with these little circles, and in fact I've highlighted one of them red and one of them yellow. And so we're supposing at the moment that we can tell the two packets of energy apart, and we can also tell the two molecules apart. So we might ask ourselves, how many different ways can we organize the molecules and the energy? And so another way of saying that is, how many microstates can we make? So you might just think about that for a second. You could pause the video and then come back to it, and I'll show you the answer in just a second. There we go. So you see in the top case there, molecule A has got both of the quanta of energy, and in the bottom case, the bottom row, molecule B has got both the quanta of energy, and in the two middle rows, A and B both have one quantum each. And since we've labelled these quanta of energy, there are two ways we could have organised them. A could have had the yellow one or the red one. So we've got four possible microstates in this system. So now we're going to look at a slightly more complicated case. We're going to build up to three quanta of energy and three molecules. But thinking back to the earlier case, what formula is it that would have given you those four microstates? So if we're looking to generalize this, we can talk about Q quanta, that's the packets of energy, added to capital N molecules. And so we're assuming at the moment that we can distinguish between all the molecules and the quanta of energy. And so we have there n to the power of q. So for one particular quantum of energy, there are n possible places it can go. So n is the number of molecules, there are n possibilities. If you add a second quantum of energy, the second quantum can go to any of the n molecules. And so the number of possible microstates, we're just multiplying n by n for each quantum of energy, which is why it's n to the power q. But now what we're going to do is we're going to say, imagine that we can't distinguish between the quanta of energy. So we'll drop the color coding. And actually this is the realistic scenario, because in practice we can't distinguish between the different quanta of energy. And so in this case of 3 quanta of energy and 3 molecules, how many microstates would there be now, assuming that the energy quanta are indistinguishable? We will still be able to distinguish between the molecules A, B and C, but not the energy. So if it was if everything was distinguishable, it would have been 3 to the power 3. But what about if the energies quanta are not distinguishable? So have a think about that. Pause the video. I'll show you the answer in a second. Well, there we are. So there's not a huge number of these. So I've just done these by hand. And the way to do this, I've taken a kind of a systematic approach here. So if you look at the top row there, are 3 quanta of energy represented by these black circles. I've initially just given them all to molecule A. And so I've just kind of done the systematic approach there, where as I go down the rows, I'm going to gradually share them out. So in the second row, I've taken one of the quanta from the first row and given it to B. And in the third row, I gave it to C instead. And so now I drop down to 1 quantum of energy in molecule A in the fourth row. So the other 2 I give it to B, but in the next case I give 1 to B and 1 to C, and in the next case I give them both to C. So having exhausted all those A possibilities with quanta, in the remaining ones I'm not going to give A any quanta of energy. So in the next one I'm going to give all 3 to B. Then after that, one of those I'm going to hand over to C, or I could have handed over 2 over to C, and then in the final row C has got them all. And so I'd recommend using a systematic approach like this, because if you go about it randomly, it's quite easy to miss one. So if we look up there, how many microstates have we got up there? That's 10 microstates, isn't it? So now we come on to working out how many microstates we can have with these indistinguishable quanta of energy. And this actually comes down to partitioning the quanta, so-called. What do we mean by partitioning the quanta? So these indistinguishable quanta, we've got to divide them up in some way between the 4 molecules available in this particular case. And so given that we're just dividing the 4 quanta up between these different molecules, we partition them using a line. So we've got the O there for each quantum of energy, and a line indicates the partition between 2 molecules. So actually, if you think about it, if you've got, say, 4 molecules, then the gaps between the molecules, as it were, are the partitions. And so the number of partitions is actually equal to the number of molecules minus 1. And so we're going to think of it in terms of these partitions, these lines, and how we can arrange the partitions and the quanta of molecules. And using this approach, we should quite effectively be able to work out how many microstates we can have with 4 molecules and 4 indistinguishable quanta of energy. So we're going to think about this in a moment. But just before we do, let me give you an example. What we've got here is the way you might write one of these microstates. So you can see that I've got the 4 O's there for the 4 quanta of energy, and the 3 lines are partitioning them between the 4 molecules. So as far as this example is concerned, you can see that each of the 4 molecules has got 1 quantum of energy. So that's what it means. And so what we're going to do now, have a think about this. You can pause the video and think about all the possible ways which you can have 4 indistinguishable quanta of energy partitioned between 4 molecules. I'll give you the answer in just a moment. Right, so there we have it on the screen. So you can see the very first example, the top left microstate. This is the one that we had in the example, where we've got one quantum of energy in each of the 4 molecules. So there's just one way we can do that. And then in the second example, one molecule, the left-hand molecule, has got 2 quanta of energy. Then molecules 2 and 3 have got 1 quantum of energy, and molecule 4 has got no quanta of energy. And what we're effectively doing is we're trying to find different ways of ordering the quanta and the partitions. And so in this scheme that we've got here, with one molecule with 2, 2 molecules with 1, and 1 molecule with 0, we can think about all the different ways we can order this up. So you might think, well, with 4 molecules, there are 4 factorial ways of ordering them. 4 factorial is 24. But we bear in mind that 2 of the molecules are going to look identical, because 2 of the molecules each have 1 quantum of energy. So the number of ways we can order this state of affairs, 1 molecule with 2 quanta, 2 molecules with 1 quanta, 1 molecule with no quanta, it's going to be 4 factorial divided by 2, the 2 being the 2 similar molecules. And 4 factorial divided by 2 is 12. And so you can see the next 12 microstates all have this feature in common. 1 molecule with 2 quanta, 2 molecules with 1, and no molecules with 0. And that takes us up to the top microstate in the middle column there. And then underneath that, we can see we've got, if you like, molecule 1 with 2 quanta of energy, molecule 2 with 2 quanta of energy, and molecules 3 and 4 with no quanta of energy. And then, again, we can order these up in as many ways as we can. So again, you might think 4 molecules, 4 factorial is 24. But 2 molecules are indistinguishable because they've each got 2 quanta. And the other 2 molecules are indistinguishable because they've each got no quanta. So the 24, the 4 factorial, we have to divide that by 2 times 2. And so that comes out as 6 possible ways of arranging it. And these are the next 6 microstates. Then after those 6 microstates, you can see we've got a 3, 1, 0, 0 type arrangement. We've got 1 molecule with 3 quanta of energy, 1 molecule with 1 quantum of energy, and then 2 molecules with no quanta. And so again, if we think about all the different ways we can order that up, 4 factorial divided by 2, because 2 of the molecules look the same, they've got no quanta. So again, there's 12 of those. So we can look at those 12. That takes us most of the way down the right-hand column until it takes us to the final 4 microstates. And in these cases, all 4 quanta of energy are with a single molecule. And there's 4 different molecules, so there's 4 different ways we can arrange that. And those are the last 4 microstates. So taking this fairly systematic approach, we've exhausted all the microstates. And if you count them up there, you can see there are 35 microstates altogether. Now, having established that there are 35 different possible microstates with 4 molecules and 4 quanta of energy, we might now think, surely there must be some kind of formula that we could have used to arrive at that. We'll need some kind of formula if we're working with much larger numbers of molecules and quanta of energy. And so in the previous case, what we were really looking at were the partitions that we were putting, as it were, between the quanta. So we're asked here, how many partitions are there between n molecules? So I think we looked at this before. They're the gaps between the molecules, so there'll be n minus 1 partitions between the n molecules. And so really what we're looking at now are just kind of the orderings that we can produce for q indistinguishable quanta and the n minus 1 partitions. And actually the partitions themselves, just being the gaps, they're indistinguishable as well. So we've got these 2 different things, the quanta, which we represent with the zeros, and the partitions, which we represent with the lines. And we're just asking, how many ways can they be arranged? And so then this becomes a sort of fairly standard maths question now about combinations. And so what we're going to find is that our 2 quantities, the q and the n minus 1, because each of them within themselves, the partitions are indistinguishable, the quanta are indistinguishable, then we simply combine the 2 together to give us our numerator. So combining the q and the n minus 1 all of those are factorials. And since the individual quanta and the individual partitions are indistinguishable, then we'll divide by those factorials so that the order they're written in doesn't matter, which is what gives us the q and the n-1 factorial on the denominator. So, just when this was making sense, we're going to make life slightly more difficult now and ask ourselves, what if the molecules are also indistinguishable? How many types of configuration are there involving 4 quanta and 4 molecules? And actually this represents a realistic situation, because we can't in practice tell the molecules apart. And so what we're going to have to do now is we're going to have to go back over all those previous 35, and then we're going to have to think about the number of quanta in each molecule. And since the molecules are going to be indistinguishable, then it makes no difference in which we write the order of the number of quanta in each molecule. And so what we're going to do is just follow a convention where we put the largest number first. That's to say the molecule first, which has the most quanta of energy. So what you could do is you could look back over our 35 microstates from before and think about how they can be categorized in terms of the number of quanta in each molecule. And then think to yourself, how are you going to write these down? We've got to do this conventional ordering that we've got there on the screen. So you might have a look back at those 35 microstates and have a go at this. Pause the video and I'll give you the answer in just a second. So there we are. There were 5 different kinds of microstate there in terms of the number of quanta of energy in the different molecules. And in fact this is quite a tricky thing to work out, this number 5 here. So I mean, we've just done it by hand. I don't think there's a simple formula for this. In practice you have to, I think, just use an algorithm on a computer to find this out. But when you look at those numbers, there's something quite interesting going on. All we're actually doing here is just dividing up the number 4 into just different sections, different parts, but no more than 4 parts, because there's 4 molecules. So in the first case we've just got the number 4, and then we divide it to 3 plus 1 and 2 plus 2 and 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. So this is called the partitions of 4. And so yeah, that's what we've got here, effectively describing our different, as it were, classes of microstate. And so the technical term for these are the configurations. There's 5 types of configuration, and this is one way of labeling them. And so this actually is a very crucial consideration when we're looking at microstates, and this is the idea of weights of configurations. So of course in reality we can't tell the quanta of energy apart, neither in practice can we tell individual molecules apart either. So in practice what we're really looking at are these configurations. So these configurations are groups of microstates where it doesn't make any difference which order we put the molecules in, because we can't distinguish between the molecules. And the number of microstates there are in each configuration we're going to call the weight. And the significance of this is, as remember we said Boltzmann had as this initial postulate, is that each individual microstate we're just going to consider to be equally likely. And so these partitions here are we're really focused on those configurations that have the largest numbers of microstates, because of course the more microstates that are associated with the configuration, the more probable it is and the more likely that we're going to observe it. And so in fact we end up using this language here where n sub 0 is the number of molecules with 0 quantum of energy, n sub 1 is the number of molecules with 1 quantum of energy, etc. And of course we're remembering that because the molecules are indistinguishable, we can order them up in any way we like. And so there we go. This was our ordering of the ordering of the molecules with the most number of quanta first. And now we're going to go on to finding the formula for the weight of a configuration. the weight W being the number of microstates of a particular configuration. And this turns out to be a really very important quantity. And so this is the number of microstates you can draw for a configuration. Effectively, it's the different ways you can order up the different molecules involved. And we've got n molecules in the microstate. So n factorial is the number of ways you can order these molecules. But actually, molecules with the same number of quanta of energy, these molecules are going to be indistinguishable. That's to say their order doesn't matter. And this is why we're dividing by the number of molecules with like quanta of energy on the denominator. So n0 is the number of molecules with 0 quanta of energy, n1 the number of molecules with one quantum of energy, etc. And so we now might ask how to go about this with the 4 quanta of energy and 4 molecules. And so what we'll do is we'll have to express each of these configurations in terms of the n0, n1, etc. That's to say the number of molecules with a given number of quanta of energy. And then once we've done that, then for each configuration we'll be able to work out the weight using the formula above. And so we're going to be ultimately partitioning our quanta in this way, categorizing it, and the table on the right up here, this is going to be how we're going to set out our work. And so you can see on the far right there, that's the weight of each configuration there, the W. So here we are. So on the left there, we've got the different configurations that we found, 5 types of configuration. And then, so for example, if you look at the top one, 4000, so that tells us that there are 3 molecules that have no quanta of energy, corresponding to the 3 zeros in the name of the configuration. And we've got 1 molecule which has got 4 quanta, and that's why there's 1 underneath the N4. And so one thing I should say, all those zeros in the table, 0 factorial is defined as 1. So effectively it means that having lots of 1s in this expression essentially just makes that term invisible. And so you see that on the right hand column there, all those different weights. If you add up all those weights, 4 plus 12 plus 6 plus 12 plus 1, that gives you 35, which is what you'd expect, because 35 was the total number of microstates that we established there would be when you've got 4 quanta of energy and 4 molecules. And so it's quite interesting when you look at this pattern, because the W there, the weight of the configuration, you see the smallest W as 1. And see, this is quite a surprising result, because that configuration we might have expected to be the most probable one. Because you've got 4 molecules, 4 quanta of energy, you think, well, they've probably got 1 quantum each. But it turns out there's actually only 1 microstate which has this arrangement, so that's actually the most unlikely one. Now, of course, the second most unlikely one is the configuration 4000, and we kind of intuitively would go along with this, because if you've got 4 quanta of energy, you think, well, it's pretty unlikely that, you know, they all end up with a single molecule. So we sort of expect that one to be less likely than the others. And so what really drops out of this is that we notice that in all likelihood some molecules have got more energy than others, and that's a kind of disordered arrangement. If you had every molecule with exactly the same energy, that represents a fairly ordered way of doing it. Likewise, if all the energy is with 1 molecule, there's a certain amount of order there as well. And so this is very consistent with this idea of entropy reflecting disorder. A disordered approach is when you neither have evenly spread out energy nor energy all concentrated in one place. On the contrary, it's kind of mixed up. So some molecules have got more energy than others. And so that's a slightly kind of disordered way of doing it. And this table makes it plain with actual numbers here. It's being very specific that we have these 2 states in particular, these 2 configurations in particular, where there's 12 microstates. These are the ones we're most likely to see because there's 12 rather than a smaller number of them. And actually, if you've come across the Boltzmann exponential function, this is kind of hinting at it, and it'll become more visible if we have more molecules and more quanta. And so what we'll do, another exercise for you, is to think, what would happen if we've got 7 quanta of energy? With more quanta, the pattern that's going to come out of this starts looking more apparent. So here you are, this is the table for 7 quanta of energy. So a fair bit of work needs to go into this. So bearing in mind that our quanta of energy are indistinguishable, we've got our factorials formula. Partitioning the quanta tells us they're going to be 120 microstates, and they can be grouped into these configurations, where in each configuration we treat the molecules as indistinguishable. And so you can see in the left hand column there, what we've effectively done is we've partitioned the number 7 into up to 4 numbers, because there are 4 molecules. They're going to take the 7 quanta of energy. And so again, if you look at these, you notice that the very top configuration, 7000, so this implies that one of the 4 molecules has got all 7 quanta of energy. So this seems like an organized state, and so the W that comes out of this 4 is relatively small compared to the other ones. Now, obviously, we can't divide 7 quanta precisely into equal numbers over 4 molecules. The closest we can get is 2, 2, 2, 1, and that's the bottom configuration. And we see also that isn't very likely. And so what we find in between these 2 extremes is some molecules having more energy than others. And what's very significant here is looking at the particular configuration which has the highest W. And you can see it's about halfway down. There's a configuration that's got a W of 24. That's to say there are 24 microstates which partition their quanta in this way, 4, 2, 1, 0. And that's quite an interesting sequence, 4, 2, 1, 0. That looks a bit like an exponential decay, doesn't it? If you halve 4, you get 2. If you halve 2, you get 1. And so the number of quanta is it's a bit like it's decaying exponentially through the numbers of molecules. And so it's no accident really that we see that kind of distribution of the numbers in the most probable state. So this is hinting at the so-called Boltzmann exponential. So there we go, that's this last point. The most probable configuration shows an exponential decay in energy across the numbers of molecules. Now, this actually links up with one of our earlier slides, S equals K ln W. And so we can start to make some sense of the master equation that Boltzmann came up with for entropy at this microscopic scale involving microstates. So you can see there Boltzmann's tombstone there. He has this equation carved into the top, S equals K log W. Now actually that looks inconsistent with the equation I've given. So in actual fact this just reflects the change in notation over the years. So what we really mean is log to the base E, the natural log. And so actually we write that ln, but back in the early 20th century when Boltzmann died, log actually was how it was written back then. So S equals K log W. And so we see here that the most likely configuration at thermal equilibrium, as we saw in the previous case, it reflects this exponential decay in the populations of atoms with increasing quanta of energy. And a curious thing are these other terms in the equation. And so what we find is, as you scale up the system with more and more molecules and more quanta of energy to a point where it starts to resemble a kind of real life situation, then the most probable configuration, it kind of grows in its relative probability. And so it becomes exceedingly more probable than the others. And so ultimately we get to the point where that particular configuration with the greatest weight, we can just assume, because of its great probability, that this will be effectively the state the system is in, or something extremely similar to it. And so this is what the W is in S equals K ln W. It's the weight of the most probable configuration. Then the K there, this is the so-called Boltzmann constant, and sometimes K sub B, because chemists use little k also to mean the rate constant. And the curious thing here is the origin of the log. So when you consider these things probabilistically, as you increase the number of particles, or the number of quanta of energy, we saw this when we saw the original formula for quanta, we're adding these numbers to the exponent. So if you double the number of particles, you'd actually be squaring you'd ultimately be, I suppose, squaring the configuration weight. And so this is why the log is put in there, because intuitively, if you think about it, we're looking for the quantity entropy. We want the quantity entropy to scale up with matter. So if you double the number of particles, you'd be wanting to double the entropy. And in fact, chemists actually express entropy as a molar quantity, which makes this explicit. And so if you take the log of the configuration weight, it will actually increase linearly with the number of particles, whereas if you didn't take the log, it would increase exponentially with the number of particles. So the log there is actually a cunning device to make entropy a quantity that scales linearly with matter. And it's for this reason that it sort of neatly fits into thermodynamics, particularly into chemistry. And yeah, moving on now, the Boltzmann constant K. So K is this kind of fundamental constant which drops out of this equation. And so it's this very small number here, 1.38 times 10 to the minus 23. And the units of the Boltzmann constant must be the units of entropy. And that's because the W, the configuration weight, is just a number, ln W is just a number. And so the K, therefore, must hold the dimensions of entropy, joules per Kelvin. And we saw in the macroscopic approach, of course, Clausius defined entropy in terms of heat added, joules, divided by the temperature in Kelvin. And so entropy, therefore, has these units of joules per Kelvin. And it's quite amazing that this quantity K is actually so ubiquitous. So in thermodynamics, we see this Boltzmann constant K in other contexts as well. And so in actual fact, it relates to the average relative kinetic energy of particles, specifically in one dimension. And what's more, when it's expressed as a molar quantity, so if you multiply the K by Avogadro's number, which is the number of particles in a mole, then the result of that is the ideal gas constant, R, in the equation PV equals nRT. So it's bizarre that when you're looking at the properties of gases, when you're looking at the properties of macroscopic systems thermodynamically, then the crucial number involved in all of this is the same number that we get looking at the microstates and relating those to entropy at the microscopic level. So it's kind of quite amazing, really, how these things all kind of line up together, despite the fact we're looking at it in very different contexts. And so I think the final thing I would mention here is to do with the Maxwell-Boltzmann distribution. This is something chemists often look at in terms of the energies of particles in a system. And so the Maxwell-Boltzmann distribution has a lot in common with the Boltzmann exponential decay that we were just considering earlier in terms of these configuration weights. And so we see the exponential decay with the Maxwell-Boltzmann distribution, but it's not quite as simple as an exponential decay, because you can see in all these three lines here, which correspond to different temperatures, in all three cases, the line actually starts at the origin and then goes up rapidly before we see the exponential decay. So you can see that as the temperature increases, if you look at the legend there, you'll see that the sort of central gravity of the graph shifts to the right as molecules tend to have more energy. But the starting at the origin is a bit surprising. And so it turns out here that it really takes into account the dimensionality. So of course molecules are moving in three-dimensional space, but when we talk about our Boltzmann exponential, especially in the context of quanta of energy, there was nothing explicit about three-dimensional space in there, was there? So really the Boltzmann exponential is something that is really tuned to just one dimension, if we had one-dimensional space. And it's when you go into higher dimensions of space that it just complicates the graph slightly, and so we start at the origin rather than starting higher up on the y-axis. And so there we go. That's why the Maxwell-Boltzmann distribution that we normally see looks slightly different to the Boltzmann exponential that we've just discovered. So now I've got a few questions for you to put into practice some of the formulae we've come across. So I'm going to give you, at slightly different context, 3 molecules and 4 quanta of energy. So we didn't look at this particular example, but if you look back over the earlier examples, it shows you what to do. And so we're going to consider these different possibilities where all the molecules and all the quanta are distinguishable. Then we're going to make the quanta of energy indistinguishable. Then we're going to consider the partitioning and the configurations and their weights. So there are a few things for you to think about.